Swayam Prabha. Digital India. Educated India.
So, in the last class, we have discussed about a measure of the size of a polymer chain different from the end-to-end distance, and the measure was the radius of gyration. So, in the today's class, I will take it further and first derive the expression for the Rg, that is the gyration radius for an ideal chain that we have discussed, and then we will talk briefly about the idea of excluded volume that I will elaborate in the following lectures. So, let us first do a recap of like what we had covered earlier. So, I said that if we have like a polymer chain, the end-to-end distance, for example, in this case is very small, that is my Re. It does not reflect the fact that the polymer occupies a large volume in space. So, a better measure is something of this sort, where what I said is that we look at an equivalent sphere that has the same volume as that occupied by the polymer chain. And then we looked at different formulas for this quantity Rg square to be more specific. Again, we are interested in the mean squared average. This was what we derived was something of this type. Which, by the way, was same as what we started with, where the center of mass location RCM is defined as and I am really summing over the positions of individual segments or beads or the actual point locations inside the polymer chain. We can define an Rg square for any polymer model depending on how I am defining my units. The i's will change. Let us say for a bead spring model, the i's can represent the position of the beads. For the freely jointed chain model, it can be, for example, the mean positions of segments. Since the number of segments are large or the number of beads are large, how exactly we are defining those particular points is not very important. In reality, in experimental case, we should think of it as every point on the polymer chain, and we should, if I do an average of this sort, I should get the Rg square, and it will not really matter so much on what model we are doing, how many segments we are modeling, provided the number of segments are large. Okay. So, now I want to look at, so this is a general expression for the Rg square average, the radius of gyration Rg. And now I want to look at how the expression will change for an ideal chain. So, of course, the expression we have derived remains the same, but we can do further simplifications if we assume an ideal chain. So, let us assume an ideal chain. An ideal chain is the one that follows the Gaussian statistics, and in so far the models of the chains that we have discussed were actually all ideal. So, then I also discussed one idea that we can go from a discrete to a continuous representation of a chain, and the idea was something of this type. So, let us say if you have let us say a freely jointed chain model and the chain looks like this, I can represent it for large number of segments as a continuous chain that is like a continuous line that is passing through it. So, of course, if the number of segments are small, there will be larger error, but if the number of segments are large, the approximation becomes I would say more just. And in any case, the polymer chain in reality is always in continuation, it is not like a discrete kind of a thing. And so, what we said is then we can talk about a contour variable. In place of talking about m segments, I can say we have a contour variable s that runs from say s equal to 0 to s equal to m. And for that particular assumption of a contour, what we can then do is we can replace the summations over the indices I and j by integrals over the contour variable. Okay. And if I now use these two relations in the earlier formula that we have derived, what I will get is, I will show on the next slide, is Rg square is actually it should be like an approximation 1 by m square 0 to u, I am sorry, it is 0 to s, and then another integration from s to m, and then we have r of s minus r of s prime whole squared integrated over ds prime and ds. Okay. Where again now in the continuous representation I am running from s equal to 0 to s equal to m, and I am referring to 2 points, one of them is my s and the other one is my s prime. Now, for the ideal chain, and that we have already discussed earlier, we know that the Rg square is proportional to the number of segments which I am sorry, this is not for the Rg square, this is for the Re square, the end to end distance squared is proportional to the number of segments. And so, if I cut my chain in here, let us say if I look at the section of the polymer chain between S and S prime, that itself is also Gaussian. Okay. So, in that sense I can represent this particular square term as something like that where we had taken a limit that b is going to 0, okay, because between s to s prime the number of segments has to be proportional to s minus s prime multiplied by a factor that we anyway assume to be small because we are going from a discrete to a continuous representation. Okay. So, now if you are with me, I can write this as b square by m square 0 to s. I have to make a small correction here. This was 0 to m because summation was from I equal to 1 to m. So, it has to be from 0 to m, and for the same reason this has to be from 0 to m. This is still the summation was from j equal to I to m. So, I am going from s to m, and then we have s minus s prime ds prime ds. Okay. So, now there is a small detail here that depending on how I am defining s and s prime, if s is higher than s prime, then we have to look at the quantity s minus s prime because that is a positive number. If s prime is however higher than s, we have to look at s prime minus s. We are essentially looking at this particular quantity, and since we are doing s prime from s to m, the s prime is assumed to be higher than s because for the s variable I am going from 0 to m, and for the s prime variable I am going from s to m. Okay. So, in that case this is really s prime minus s. Okay. So, now to do the integration I will define a new variable. Let us call this s double prime. This is equal to s prime minus s, and then if I do a ds double prime, that is equal to ds prime if I am interested in doing the inner integration. So, for the inner integration I am looking at s prime. So, I want to convert s prime to s double prime integration, and for that reason I write these two relations, and the limits of the inner integration will change. So, this will be so now earlier it was for s prime, now it is for s double prime. So, we have to do a minus s for the limits as well. So, this becomes 0 and this upper limit becomes m minus s, and now we have s double prime ds double prime ds. Okay. So, now if I look at the inner integration, that becomes m minus s squared by 2, and anyway the lower limit is 0. So, now I am left with okay. So, I can apply the same idea again. I can think of a new dummy variable, that is let us say s of triple prime, and let us say that is m minus s. So, now we will have ds of triple prime is equal to minus of ds. So, now I will have my integration as, so now that it is m minus s. So, the lower limit is m, the upper limit is 0, and then we have s triple prime square ds triple prime with but a negative sign, but now I can use the minus to switch the upper and lower limits, and so we have basically and then we have an m cube by 3 here, and that gives me, we have certain cancellations, mb square by 6, which really means re square by 6, because re square averaged is mb square. So, if I divide by 6, we get the rg square average. So, what we have derived is for an ideal chain rg square is re square by 6, again ensemble averaged, and then this is equal to mb square by 6. So, now there may be a bit of an confusion here, because we said that I want to define a new kind of an average, and the new average will look at the volume occupied by the chain in place of the end to end distance. Okay. And then what we figured out is actually what we get is the mean square of this quantity is anyway the mean square of the end to end distance divided by 6. So, both are essentially related, but this may not be possible if I think of other kind of chain models. Okay. And that is where this quantity become useful. That is one thing to make here. The other thing to make out from here is we are not saying that the end to end distance of the chain in a particular configuration. So, in a given configuration, of course, this can be my Re and this can be my Rg, they can be very much different, but if I take an ensemble average over them, over the squared value of both of them, then they are related. Okay. So, there can be cases where end to end distance is small for a particular configuration, for other configuration or conformation it can be very different. Okay. But if I take a mean squared averaged, then the number I will get is related to the mean square average of the Rg as well. Okay. So, they are related only in the sense of the ensemble average, they are not related in the sense of a particular configuration. So, volume occupied by a configuration is given by the Rg, and that will be different than the Re in most cases. Okay. So, now I now want to take another. So, I now want to just give you a demonstration of what happens if the chain is not ideal, okay, and how does we proceed with calculation of the radius of gyration and actually square of it. Since we have derived couple of formulas in the previous class, we will see how does different formulas find their use in terms of mathematical simplicity depending on the problem at hand. So, in this case that we discussed, for an ideal chain we have used this particular formula. Now, I will show that if I want to look at say some other type of change, this other formula can also be useful. Okay. So, let me take an example of a polymer that is like a rod, that is a very stiff polymer that is like pretty much like a rod. Okay. So, it is not an ideal chain, it is very stiff. Actually, this model really applies to things like DNA, which is really very stiff molecule, in that case if I look at many conformations, there will be slight differences, but by and large the chain looks pretty straight. Okay. So, if I have a rod like polymer, again I can use the idea of defining a contour variable s running from 0 to m, But now it is very easy to identify where my center of mass is. It is right at the center, and we know the location of it, and that is m by 2. Okay. So, if I now include the b variable, we know for the fact that RCM has to be m by 2 multiplied by b. So, in this case we do not have to go to calculate RCM in detail, we know it is a straight rod. So, we know the center of mass. So, it is very convenient to use the first formula that we started with. So, now the Rg squared is so, keep in mind that in this case I am not even looking at the ensemble average, because there is only one conformation of the chain, and that is like a rod, and there are no other conformations. We can look at actual the Rg values, and this idea really extends to objects of any shape. Actually, that is where it is coming from, that we can define radius of gyration of objects of different shape. We are applying to polymer physics, and then we get different results, but that idea itself is very general. So, now with the same kind of discrete to continuous representation, I can replace the summation by an integration from 0 to m, and I will have u minus m by 2. Let us keep the same variable s, and then we had a b square coming in front, and this has to be integrated with respect to s. Again I can say that I will represent s minus m by 2 as, say, s prime, the standard variable transformation, and then ds will become same as ds prime, and so Rg square will be, the limits is s minus m by 2. So, it is 0 minus m by 2 is minus m by 2, and m minus m by 2 is m by 2. So, s prime square ds prime, ds is same as ds prime. So, this is equal to so, of course, both the upper limit and lower limit are the same, but differ in sign. So, if I take the upper minus lower, we get double of the same quantity. So, we get b square by m multiplied by 2, and then m by 2 cubed is m cube by 8, and we had a 3 here. So, it is 24, and so we get okay. So, now of course, instead of the Rg squared going like m, now it is going like m squared. That is the kind of behavior we expect in the rod like chain. Essentially what it means is, now I can also define the length of the rod as L being equal to m of time by times b. So, it should be L squared by 12, that is a different kind of scaling than compared to the ideal chain that we see in the case of a rod like polymer. So, the purpose of this was simply to demonstrate how do we go ahead and calculate the radius of gyration for different kind of shape. You can try the examples for, say, disc, cylinders and so on, and that will give you an understanding of how the volume occupied by objects change for as a function of the geometric variables that you have. Okay. So, now very briefly I want to discuss an idea that we left earlier, for the want of a better word. What we are talking about is something like the chains, the segments of a chain which are far off along the contour, they can also come together and interact, okay? And that is not being covered in the ideal chain models we have discussed. So, of course, we say that if I have a polymer chain like this, then for short range or short distances along the contour, the correlations are present, but as long as the correlations decay with the distance along the contour, the chain is ideal. Okay. So, if I say look at two particular points S and say S prime. Now, these 2 points are, although they look physically close and they may be physically close, but they are very far off along the contour. If I have to find the contour distance between them, I have to essentially compute the distance that I am drawing like this. So, this yellow part indicate the distance along the contour. On the other hand, the physical distance can simply be this. Okay. So, when I look at say my S minus S prime, that represents the distance along contour, and what we said is if correlations between segments decay rapidly with distance along contour, in the figure that we have just put in, that is equal to S minus S prime, then the chain is ideal. That is, we have the scaling R E square proportional to m. In fact, as we just derived, R G square also goes like m. Now, what do we mean by these correlations? So, if you remember from the in the very beginning, I said that if I look at the actually at a molecular level, they come from the fact that the adjacent carbons share a covalent bond, and that is the reason why this bond distance is very less flexible. If I look at say a particular angle, let us say this theta between 3 carbons, now it is no longer as stiff like a bond, but still we have an overlap of electron clouds here, overlap of electron clouds here. The electron clouds represent the covalent bond, and these 2 electron clouds have some interaction between them, and so theta is more flexible than B naught, but still not so flexible. However, if I look at say between 4 carbons, I said we can define what is known as a torsion angle or a dihedral angle. Now, they are relatively more flexible. We can have rotations around the carbon-carbon bond, and that is how we get different conformations. Okay. So, the main idea was that if I go along the carbon chain, at short distances we have strong bonded interactions, and at long distances the bonded interactions decay, because between two adjacent carbons we have covalent bond sharing, between three we have overlap of two clouds of electrons, that is between the two carbon carbon bonds that we had, and then between say 4 carbon atom in a series we have a torsion that is relatively more flexible, we can have rotations around it. And if I think of say a 5 carbon, let us say between a carbon A and say A plus 1, A plus 2, A plus 3, A plus 4, A plus 5. Now, between A and A plus 5 it is even less correlations. What it means is the position of these two are less correlated, or they can be varied relatively more easily, or they can actually, if I really extend the idea to say 20 or 30 carbons, we can start to see that there is almost no correlation, in what case I can pretty much choose the position of a carbon distant along the chain independent of where my carbon is far off along the chain. Okay. Now, what we missed here is something that is known as a non-bonded interaction. Okay. So, of course, electron cloud layering gives rise to bonded interactions, overlap of clouds give rise to say an angle interaction and so on, but that is not the only interaction that are present in the system. For example, you can have a situation where you have a negative charge here and a positive charge here. Now, these two guys, even if they are distant along the contour, since they are physically close and they have opposite charges, there will be large attraction between them, which is not being considered in the ideal chain model. Okay. Now, Coulomb interactions is not the only interaction, again you can have other interactions which can be relatively less strong than Coulomb, but they appear in most cases. One of them is known as the van der Waals interactions, which is relatively weaker than Coulomb, but it is not something that is weak enough to be ignored. Okay. So, in that case we also have to account for this. So, as when we discuss the ideal chain models, what essentially we are saying is the non-bonded interactions are not included, and unlike the bonded interactions that vary with the distance along the contour, so the bonded interactions vary with the distance along the contour, the non-bonded interactions vary with physical distance, which can be more precisely that physical distance will be the difference in the positions of segment S and S minus S prime, and the distance along the contour is absolute value of S minus S prime. Okay. So, this is where we will define the idea of excluded volume and see like what implications it has on the behavior of the polymer chain. So, I will close with this and then we continue the discussion in the next lecture.